Good morning, students. Let us have a brief recap of what we were discussing yesterday. Yesterday, we were discussing the solution of this particular exercise. Uh, Let me read this example once again. A telephone link having a bandwidth of 3 kilohertz means B is given here. You remember the Shannon-Hartley law. C equals B into Lg of 1 plus S by N. So B, bandwidth is given here. SNR of 13 dB. So S by N is given in decibels as 13 dB. At a rate of 1200 bits per second means the source encoder's data rate is given here. That means small rs is given here. It is provided with a modem that can operate at 3600 bps. Means a modem is going to add the check bits, or the modem is going to have a channel encoding scheme inside. So the modem can operate at 3600 bps. That means the data rate at the output of the channel encoder is given as 3.6 kbps. Then the error probability is given as 8 into 10 power minus 4. Generally, we have something called BER in the communication theory. Bit error rate means if at all we transmit 1000 bits, out of 1000 bits, how many bits had an error? That way, a statistical average is calculated. The lesser the BER, the better is the communication. That is the conclusion. Ideally, BER has to be 0, but that is not possible. So, in general, bit error rate is always 10 power minus 2 or minus 3 or minus 4. That way they measure. The lesser the value of BER, the better is the communication. So that way here, error probability is given as QC equals 8 into 10 power minus 4. Which simply means that one bit is sent, what is the error of that particular bit being flipped? That is 8 into 10 power minus 4 for this given system. It is desired to design an error control coding scheme having overall probability of error less than 10 power minus 4, which means we want to have an error which is 10 power minus 4. Now the error probability given is 8 times more, that is 8 into 10 power minus 4. So we have to find out how can we achieve a lesser error for the given communication system. This was the discussion yesterday, and I had discussed the solution also. RB given is 1.2 kbps, RC given is 3.6 kbps, B is 3 kilohertz, and probability of dk cap not equal to dk. Dk cap is the bit received at the destination. dk is the bit transmitted at the source. That is QC equals 8 into 10 power minus 4. Desired probability of error if is P of bk cap not equal to bk is 10 power minus 4. That means after we receive at the source decoder, we want an error probability of 10 power minus 4, which means the channel encoder should have a scheme where the channel decoder will have a reduced error probability. Please remember, whenever we use this dk, that indicates the data that is coming out of the channel encoder, and whenever we indicate bk, that is indicating the bits that are coming out of the source encoder. So S by N is already given as 13 dB. Now when we convert into actual number, it is 19.953. So applying the Shannon-Hartley law, we have C equals 3000 into Lg of 1 plus 19.953 is 13.169 kbps. Now as our RC, or the channel encoder's data rate, is 3.6 kbps, and as the channel capacity is much larger, we surely know that it is possible to transmit the data by means of a suitable coding technique with a small probability of error. That is what the second theorem of Shannon says, that as long as the channel capacity is not exceeded, it is possible to transmit the data with the reduced number of error bits. So all this I had discussed already yesterday. I am just going through it once again so as to have a recall of yesterday's concepts. We have RC equals RB into N by K, where N is the total number of bits that are coming out of the channel encoder in a block, and K is called as the block size in the source encoder. Means if at all we send 8 bits, let us say we add additional 4 bits, then N will be 12 bits, K will be 8 bits. That K is called as the block size. So naturally we have this RC equals RB into N by K, or 3600 equals 1200 into N by K, or N by K is now 3. Now for K equals 1, let us say for every 1 bit, we have total number N is 3. That means for every 1 bit of information, we should add 2 check bits. Anyhow, it is given that modem can have 3.6 kbps and the source is having 1.2 kbps. So safely we can add additional 2 bits. So the number of check bits N minus K is 3 minus 1 equals 2. So if a message bit 0 is transmitted, then 000 needs to be sent out of the channel encoder. Similarly, if a message bit 1 is transmitted, 111 has to be sent out of the channel encoder. We are replicating the same bit twice. Now the other 2 bits that are added are actually check bits. Now let us see how the channel decoder is going to decode the data. The noise in the channel may affect these bits during transmission. Let us suppose that the receiver decodes the received code word by using a majority logic scheme as shown. This is the majority logic scheme. That means which bit is occurring at least twice. Based on that, the source decoder will come to a conclusion. So 001, there's a 1 bit error. 010, 1 bit error. 011, again 1 bit error. Majority logic is 1. 100, 1 bit error, output is 0. 101, output is 1. 110, output is 1. 111, anyhow, output is 1. This is where majority logic is applied. But there are chances that complete 111 itself may be erratic. If at all 000 is transmitted, noise may be induced in the channel and the source decoder may decode it as 111 itself. That chance is also there. All the 3 bits may be under error. Or if 111 is transmitted, all the 3 bits may be under error and only 000 may be decoded in the source decoder. Such chances are also there. But what is the probability of such chances? That is rare. Let us see that later on. So here 000 and 111 are the only valid code words and the others are affected by noise, either by 1 bit or by 2 bits. Even 000 and 111 also may be affected by all the 3 bits. But as we have adopted the majority logic scheme, the overall probability of error is given by PE equals P of BK cap not equal to BK, that is at the source decoder. That is probability of number of errors greater than or equal to 2. As we have 2 check bits here, out of 3 bits, if there are 2 bits under error, then we should calculate that probability of error. So let us continue with this now. Let this capital X be the random variable representing the number of errors. Then capital X is a binomial variable with n equals 3 and that probability is nothing but QC that is given. So please recall the binomial theorem where we can express this probability of error as the probability of X remaining greater than or equal to 2. That is summation of x equals 2 to 3, because the number of errors can be 2 bits where all the 3 bits also can be also under error. So summation of x equals 2 to 3 of ncx into p power x into 1 minus p to the power of n minus x. This is as per the binomial theorem. Now this is nothing but summation of x equals 2 to 3, 3cx qc to the power of x 1 minus qc to the power of 3 minus x. Now when we expand this, we get PE equals, let me show you the complete value, PE equals 3c2 into 0.0008 whole squared into 0.9992 to the power of 1. Same way when we continue, 3c3 into 0.0008 whole cubed into 0.9992 whole squared. that is given as QC is 8 into 10 power minus 4. It is directly substituted here. That is nothing but 3C2 is 3 factorial divided by 1 factorial into 2 factorial into this particular value, plus 3C3 is 3 factorial divided by 0 factorial into 3 factorial into this particular value. So we get 1.919 into 10 power minus 6 for the schema of this majority logic. So as this 1.919 into 10 power minus 6 is less than 10 power minus 4, the system was given with the probability of error of as 8 into 10 power minus 4. What we wanted was a probability of error of 10 power minus 4. Now by adding the additional 2 check bits, we calculated the total error. That error is 1.919 into 10 power minus 6, which is much less than 10 power minus 4. So this particular error control coding scheme is quite satisfactory in performance. Now without the error control coding, the probability of error was 8 into 10 power minus 4, and with error control coding, it is reduced to 1.919 into 10 power minus 6. So for 1 bit of information, we are adding 2 check bits, and this error is, I should say, the error is drastically reduced. We can take it as 2 into 10 power minus 6, whereas earlier it was given as 8 into 10 power minus 4. Now 8 into 10 power minus 4 is reduced to 2 into 10 power minus 6. So we should say that the error is drastically reduced. Still, you may have a question now. Let us say if all that 000 is affected by noise, and at the receiver, if it is 111, it will be decoded as 1. Now instead of 0, the destination has detected as 1. Now that is an error. Yes, that is an error. That is why here we have error 1.919 into 10 power minus 6. Error can still occur because we cannot have an ideal channel. Error can still occur, but the probability of such error is really very less. That is the point here. Now the question is, if such error is occurring there, what can happen is the next question. In spite of adding 2 check bits for 1 information bits also, now if we have this error at the destination, then it means that how the error can be corrected at the destination if such error is occurring. The point is, we will have to live with such error in such cases. For example, when you buy a DVD, in the DVD, let us say there are some scratches or there is a slight damage, and there can be some erratic information there. Whatever is stored as 1 may be decoded as 0 because of the scratch on the DVD. Still, that error will be there always. There is a certain amount of probability of error. That error will be there always. That error has to be there even when the DVD is played. Now the point is, you will not be able to detect the error when you are watching the movie or listening to the song. Why? Because the DVD is playing at a high speed and it is transmitting data maybe in kilobits per second, megabits per second, or even gigabits per second. Whereas we are perceiving this particular data through our sense of vision or sense of hearing, we have our own limitations. Our sense organs are having a response speed in milliseconds, whereas the technical equipment is working in microseconds and nanoseconds and picoseconds. In such a case, even if a 1 or 2 bits errors are there, that will not be noticed by us. That is the point here. Whenever the electronic equipments are working at a much faster speed than the human beings themselves, then will the human beings be able to detect the error is the point. There is a funny story of somebody beating a buffalo. A buffalo was sleeping in the pond, and the buffalo had forgotten that it has to go back home. The owner of the buffalo came there and he saw the buffalo in the middle of the pond. He started calling the buffalo, but the buffalo was in a highly joyous mood inside water. Buffalo did not notice its owner calling it. Now the owner picked up a stick and standing at the shore of the pond, he tried to beat the buffalo. But the stick was not reaching the buffalo. So he went a little deeper into water. He started beating the buffalo, but still he was at a distance from the buffalo. Even though stick was reaching the buffalo, buffalo did not actually understand what was happening. Buffalo was thinking, somewhere something is happening. Somewhere somebody is doing something. Because buffalo was thick-skinned. After a few minutes, this person became desperate. He went slightly more nearer to the buffalo. He started beating the buffalo with the more force now. Now the buffalo started thinking, somewhere somebody is hitting somebody. Still, it did not understand that its owner is beating it because the pressure or the impact of the beat was not enough. Now the person went very much nearer to the buffalo and he started beating the buffalo with the highest force with which he can be beating it. He wanted the buffalo to come out of the pond and he wanted it to come back home. Now when he was beating with the highest pressure, even though he was at a deeper water now, and the buffalo was enjoying the water's contact there. Now when this person was beating, the buffalo had a much higher force, and now the buffalo understood that, oh, my owner himself is beating me. In the same way, when the technical equipments are working in a threshold which human beings cannot really sense, or when the technical equipments are working in a speed with which the human beings cannot really sense, then even if that error is there, that error can be tolerated. That is the idea here. So at times, we will have to tolerate this small amount of error probability also. The question is, how can we eliminate complete error? We cannot eliminate complete error. If we have to eliminate complete error, then we should not use a channel at all. Okay. If the source and the destination are adjacent to each other, then there can be no noise induced at all. Otherwise, any communication channel will be inducing noise. Noise is part of nature. As noise is part of nature, we cannot have a completely noise-free channel. Okay? Even if we use a best quality optical fiber also, even if you use the best quality optical fiber, let us say we use this optical fiber for making a call from India to USA. Imagine, when we have a international call from India to USA, it is going through the best quality optical fiber. Still, we cannot have a single fiber laid between USA to India, right? It's impossible. At so many places, we will have joints where some length of optical fiber will be joined through some other equipment. And as we cannot have a single optical fiber all the way, as we have joints in between, even the joints cannot be perfect joints there. And wherever there are joints, there can be a certain loss of light. Inside the optical fiber, it is the light that is moving. So there can be certain loss of light. Moreover, when the light is traveling through total internal reflection inside the fiber, even the fiber will have its own attenuating properties for the light. So wherever the light intensity is reduced, on the way we should have light amplifiers installed for the optical fiber cable. So that way, even the best quality optical fiber will also have attenuation, it will have loss, it will have other joint related losses. There are propagation losses, there are bending losses. You are going to measure these losses gradually when you work in the communication lab. In the communication lab, you have experiments on optical fibers. So that way, we cannot completely have a error-free communication. If at all we should have error-free communication, channel should not be there, source and destination should be together. That is the only way. Otherwise, in almost all of these communication setups, we will have a certain probability of error and sometimes we tolerate it. Okay. So here you can see that the error is reduced to approximately 2 into 10 power minus 6. But what was the overhead? The overhead was, instead of 1 bit, additionally we added 2 bits and we were transmitting 3 bits. It is as if you want to throw a stone at a mango, and with the particular throw of the stone, you want the mango to come down from the tree. Now, let us say instead of 1 stone, let us say you have 3 stones, and you will aim at the mango. First, you will throw first stone, then second stone, then third stone. There is a high probability that out of these 3 stones, at least 1 stone will hit the mango. If at all the 3 stones are not hitting the mango, then what will you do? You will pick another 3 stones and try to get that mango, or else you will get exhausted and you will go away. You have only these 2 choices now. So let us say there is a high probability that when you throw these 3 stones and you are aiming at the mango, at least 1 stone will hit the mango. That way, still there is a probability of error. Now, you hitting 1 stone to the mango has a larger probability of error. You hitting 3 stones to the mango has a lesser probability of error. Now, that is the overhead which we have to handle, because ultimately we want the mango to be coming down from the mango tree and we want to taste the mango. That is the idea. So, as such, whatever is in nature, the same thing is applied in technology. I have been telling you, most of those inventions which human beings have developed is basically the replication of whatever nature has already developed. Technology is nothing new. Whatever technology is there, it is already there in nature in some other way that we are applying to science and engineering and technology. Now let me proceed. We have seen one particular scheme here called majority scheme. Now let us discuss this a little more so that later on we will develop some other algorithm for error detection and correction. The methods of controlling errors. In the previous example, the receiver has 2 valid message sequences, 000 and 111. These 2 are 100% valid messages. If the receiver receives any other sequence, then the receiver has 2 choices. One is to apply the majority logic scheme and to decode, then to discard the received message and to ask the transmitter to resend the message. I had told you earlier about this ARQ, automatic repeat request. To discard the received message and to ask the transmitter to resend the message. Now this first option is called as forward acting error correction, and the second option is called as error detection. See, the first option is called as forward acting error correction, which means when the bit stream is received at the receiver, let it detect the error, let it correct the error without actually communicating back to the transmitter. That is called forward acting error correction. Why is it called as forward acting? Means data is forwarded to the destination. At the destination itself, error correction is happening without any intervention between source and destination. That means the destination will not communicate back to the source. That is called forward acting error correction. And the second option is the receiver asking the transmitter to send the data back. Now, the receiver has detected the error. If it has not received 000 or 111, that means it has detected the error that I have not received 3 zeros, I have not received 3 ones, I have received something else which is a combination of 0 and 1. That means there is a error. And the destination will say to the source, you send it back because I have an error. That is called error detection. Now, the second option yields a lower probability of error than the first one. Why? Whenever error is detected, the receiver will tell to the transmitter that send the data back to me, there is an error. Until the correct data is received, that means either 000 has to be received or 111 has to be received. Until then, the receiver will not decode the data at all. So that way, the second option has a lesser probability of error than the first one. But what is the overhead? Overhead is time is lost in this manner. For example, let us say you and me are communicating and my speech is not being properly received to you. Now you have two options. Based on whatever speech is received to you, you can decipher that I am talking this particular word only. That is forward acting error correction from your side. Otherwise, you have the option to keep on telling that, pardon me, sir, I did not correctly understand what you told. And you can keep on telling me, pardon me, pardon me. And that way, when you say pardon me, I'm going to repeat the same sentence again. And again, if there is error, again you will keep on saying pardon me. So that way, until you fully receive the sentence which I speak, in between you and me, there is this time being wasted. That is the overhead. Whether the time is being wasted or the time is being utilized, we don't know. But the time is taken is more for the purpose of transmission of data. That is the problem with the second option. That is the problem always with the ARQ scheme, automatic repeat request scheme. So the best option is what? First option, forward acting error correction. That means when you receive the data, let us say when you receive the speech from my side, let us say there is certain amount of error in the speech which you received, but you are intelligent enough to relate all those wordings, and you are intelligent enough, let us say, to find out what may be the sentence which I spoke. I had shown you two slides earlier, even though they were humorous or funny slides. I had shown you that human beings have the ability to presume things and to correct things on their side also. So let us say you are also an English language expert and you can easily find out what would have been the wordings which I used in the sentence which I am speaking. And even if there is an error in between, maybe a few signals are gone or maybe a few pronunciations are gone. In spite of that, it is possible that you will relate all that and you will have a correct sentence at your side. That is called forward acting error correction. Now, we are going to go for the first option only, that is forward acting error correction. We are not going to go for the second option. Now, again, the question may come that if at all we are going for the forward acting error correction, what happens if there is a large amount of error? Right now, we are not going to deal with that particular method of large amount of errors handling. That large amount of errors handling is called as burst error handling. I am going to discuss about burst error later on, but we will not have a methodology in this particular course to handle the burst error, because you are going to study a course called wireless communication in the 7th semester. There you remember this burst errors handling, and there you are going to learn more about how to actually correct the burst error. Which means, let us say I am speaking to you, let us say nearly 75% of my sentence is not received at your side. Imagine that way. Maybe because of the network issue, maybe because of the noise, whatever I am speaking, nearly 75% is not received. Now that is called as burst error. If that 75% also is not received, what to do at the receiver side is a bigger challenge there. There is a method called interleaving, there is a method called block interleaving, where sometimes the data is stored column wise and data is sent row wise, or it can be vice versa also. Data can be stored row wise, data can be sent column wise, and at the other end the reverse will happen. And that way, when the data is stored row wise, when it is sent column wise, what happens there is, even if there's a burst error, if a complete row is gone also, the receiver is going to receive a column. Column by column it is going to receive, and it is going to again arrange it back row by row. Whenever it receives a column, it can always correct a 1-bit error. Imagine if the complete row, let us say, complete row contains, let us say, 2 bytes or 16 bits. In 16 bits, let us say 12 bits are lost because of error. Such error is called burst error. This happens during lightning or thunder or rain. In such cases, burst error occurs. Now, if such errors are occurring, out of 16 bits, 12 bits are lost. What method or technique can be followed is, instead of sending the row as it is, column is sent in the memory, and the column is received at the receiver, and the column is decoded. Now, in the column, you will not have 12 bits error. You will have only 1 bit error, right? Even though in the complete row it was 12 bits error, in a particular column there can be only 1 bit error. That 1 bit error can be detected and corrected. Later on in the receiver, the reverse method will happen, where all columns will be taken out and again decoded as rows, and that 1 bit error would have been corrected in the column. That is called as one method of interleaving. But there the overhead is that until the complete memory is full, transmission cannot happen. Until the complete memory is full, even at the receiver, decoding will not happen. That particular timing is called latency or delay. That latency has to be compromised there to overcome the burst error. I have briefly told you about how to handle the burst error, but if you did not understand it fully now, you will have to wait till 7th semester where you study this in more detail, because you are going to study the complete cell phones architecture or complete wireless transceivers architecture there. There you are going to learn more about spread spectrum, more about voice coding, voice decoding, vocoding concepts. You are going to study more about all those things. So, we will not be going for the second option now. We will be going for the first option only, because time between receiver and transmitter is going to be saved. Why? The reason is, if there are two human beings communicating, they can keep saying pardon me, and the transmitter can keep repeating the same sentence. But now when two machines are communicating, we cannot expect that there will be a ARQ protocol between receiver and transmitter where a lot of time is lost in this communication itself. So machine must be made more intelligent to detect the error and to correct the error. So we will be going for the first option itself. Now, for example, in the previous example, if all the 3 bits are in error, then the receiver is unable to detect the error. Hence, the probability of error is QC cubed, because it's 1 bit error cubed, that is 5.12 into 10 power minus 10. This value is much lesser. Compared to that 8 into 10 power minus 4, this is still lesser. It is much lesser. However, the communication becomes slower in case of the other 6 messages due to the wait at the transmitter for acknowledgement before transmitting the next message. So, whenever a transmitter sends 3 bits, it has to wait for acknowledgement from the receiver. And once the acknowledgement is, let us say yes, then the transmitter will send the next set of bits. Let us say the acknowledgement is no from the receiver side, then the transmitter will send the same 3 bits once again. So there will be a delay always, as the transmitter is waiting for the acknowledgement. So that way, there is a summary or a tabulation. Error detection, probability of error is lesser, and a reverse channel is present here. What is meant by reverse channel? From the receiver to the transmitter, there must be one more channel present, so that the receiver will say, I have detected and I have either obtained the correct message or I have obtained the erratic message. Now it says, I have obtained the erratic message, send it once again. So that way, reverse channel is required between transmitter and receiver in case of the second option, that is error detection, where the speed is going to be naturally slower. Whereas in case of error correction, the probability of error is larger. But reverse channel is not there. We don't have to invest more for the resources now, and the speed is faster. So we will be discussing the error correction method only in this particular module. Let me proceed now. Of course, the choice of the method depends on the particular application. However, in case of modern communication receivers and for real-time applications, it is desirable to make the receiver intelligent enough to detect and to correct the errors at the receiving end itself. Now, look at this. Let me annotate. In case of modern communication receivers and for real-time applications. So the choice of the method depends on the particular application. But the modern communication receivers can have a large amount of memory and they can work at larger speed as well because of the advent of VLSI. I met one of my old students in a function last week. He works in a company called Qualcomm now and he is in the design team. I casually asked him, what is the progress happening right now in the VLSI domain? Then he told that right now we are working with the 3 nanometer technology. Whereas in our lab in the college, we have 180 nanometer, 90 nanometer and 45 nanometer technologies available in the Cadence tool. Whereas he is telling, now we are working on the 3 nanometer technology. I asked which tool? He said same Cadence tool only. That means Cadence has developed its own libraries even for a 3 nanometer MOSFET. Then I casually asked him, if you are working on 3 nanometer, maybe after about 10 years, what may happen? Then he said, sir, nanometer will move into picometer, sir, he said. Because from micrometer, we moved on to nanometer. Now from nanometer, we will move on to picometer. And we will develop some methodologies in future. We don't know what may be there in future, but people will keep on working. Now think about it. If a transistor can be having a dimension in picometer size, now we can have a large amount of memory integrated into a smaller area. And in such a case, our communication receivers as well as transmitters can have a large amount of memory. And as the switches are smaller in size, they can work at a larger speed also. So larger memory, larger speed, both are there in case of our communication equipments. Actually, we want real-time applications only, right? Real-time applications means between the transmitter and the receiver, we don't want any latency or delay as such. Because the delay will affect the normal communication process itself. So it is possible that we will make our communication equipments more intelligent so as to suit real-time applications. So it is desirable to make the receiver intelligent enough to detect the errors and to correct the errors at the receiving end itself. That way, the transmitter will not bother about whether the data is received there at the receiver or not. The transmitter will simply keep on transmitting the data. Receiver will keep on receiving the data, it will keep on detecting and correcting the errors and it will go for channel decoding and source decoding. This is what is going on in the present communication scenario. But why is it told that the choice of the method depends on the particular application? There are methods of communication called simplex, half duplex, full duplex. Simplex means only one-way communication. Transmitter will transmit, receiver will receive. Just like the SMS is basically simplex. SMS or WhatsApp message, I simply type in my phone and it is received at the destination's end. That is simplex. Whereas half duplex means between you and me, when I talk, you listen, later on you talk, I listen, then that is half duplex. We are using the same communication channel in between two of us. But when I talk, you will not listen. When you talk, I will not listen. That is called half duplex. Full duplex means both will keep on communicating with the two channels. Of course, that is not possible with us now as human beings, but machines can do it. As a full duplex communication means there can be two channels now, one transmit channel, one receive channel. And the transmitter will receive also, receiver will transmit also at the same time. Then we call it as transceiver. It is not just transmitter and receiver, it is transceivers where there can be two processors, two co-processors with the main processor. One processor for transmitting, one processor for receiving, two co-processors along with the main processor. There can be transceivers working simultaneously. That is called as full duplex communication. So the choice of the method depends on the particular application. Means if it is only a simplex communication, then there cannot be receiver transmitting back to the transmitter with the ARQ channel. So then the receiver, if there is error, the receiver itself has to detect the error and correct the error. If it is half duplex communication, then it is possible that receiver will only detect the error, it will not correct the error, it will ask the transmitter to send the data back. There is a reverse channel there. That is possible. But what about full duplex communication? In case of full duplex communication, both are intelligent machines. Both sides, transmitting and receiving, both are happening. There can be high level of protocol schemes among them, or both can be able to detect and correct errors always. It depends on how much of intelligence is put into those machines. Anyway, nowadays, due to the advent of artificial intelligence, machines are learning more than humans. And I'm happy to say that in our college now, we have started a new branch called AI and ML, Artificial Intelligence and Machine Learning, which is going to have a much bigger impact on human life in future. In future, maybe when you go to a market, you may, instead of a security guard, you may greet one robo. That robo itself is working like a security guard there. The robo will be scanning you, not by really touching you. It will just scan you through its own electromagnetic waveforms maybe. And it will immediately detect whatever is having inside your body without actually touching you. So this way, in future, maybe in the next 20, 30, 40 years, due to the advent of AI and ML, things may drastically change. We don't know. I may not be there to see all that. You will still be there to see all that. Anyway, let me continue. Let us see the types of errors now. When white Gaussian noise is present, the error occurring during a particular interval does not affect the transmission during the subsequent interval. Just understand this. When white Gaussian noise is present, the error occurring during a particular interval does not affect the transmission during the subsequent interval. Such errors are called random errors. Means I am sending a block now, I will be sending the next block later on, and the white Gaussian noise is uniformly affecting all the blocks that way. But this noise is affecting only a particular block at one time, because it's a timed transmission now. So the error occurring during a particular interval will not affect the transmission during the subsequent interval. That white Gaussian noise may not be present during the next interval also, because noise is random. Such errors are called as random errors. On the other hand, the impulse noise affects more than one symbol. For example, if a lightning is occurring, or a rain or thunder is occurring, it will last, let us say, for a few seconds. Now we are dealing with the communication system which is working in microseconds and nanoseconds. So if lightning occurs even for a few seconds, it is continuously occurring there. When it is continuously occurring there, it may affect the complete block there. That is what is meant here. The impulse noise affects more than one symbol, and hence there is dependency of error in the successive symbols also. Such errors are called burst errors. Error control schemes should deal with both types of errors. Now, let me underline these random errors and let me underline these burst errors. In this particular course, we are dealing only with the random errors. We are not dealing with burst errors. I gave you an example of an interleaving technique to correct the burst errors by storing in rows and sending in columns, and then again receiving in columns and arranging back in rows. That is one good mechanism of overcoming or correcting the burst errors. But in our course, we are not dealing with burst errors. We are dealing with random errors only. So, what we will do in the future classes is, we will discuss a method called block coding method, where one block of data is sent. For that one block of data, how the error happens and how we detect the error in that one block of data, how we correct the error by using matrices as well as mathematics. We will see that in the next class. as it is time now, I'll end the class for today. Anyhow, we are not going to deal much with burst errors. We will be dealing only with random errors. Please bear this in mind. See you in the next class. Until then, take care and goodbye.